Curse of dimensionality. The required number of samples to achieve the same accuracy grows exponentially with the number of variables. But in practice, number of training examples is fixed. So we have a fixed set of data, but the required number of samples grows exponentially with the number of variables. So the more the number of variables, we require more data to achieve the same accuracy, but the data is fixed. This is the curse of dimensionality. Therefore, the classifier's performance usually will degrade for a large number of features. So given more variables of independent variables or features, the classifier performance will degrade over a large number of independent variables. Covariance and variance. Variance and covariance are a measure of the spread of a set of points around their center of mass, or mean. Variance is a measure of the deviation from the mean of points in one dimension, example heights. Covariance is a measure of how much each of the dimensions vary from the mean with respect to each other. So covariance is in terms with dimensions and variance is in terms with points. Covariance is measured between two dimensions to check if there is a relationship between the two dimensions or not. Example, the number of hours studied and marks obtained. So if considering we have a three-dimensional data set, then one could measure the covariance between the x and y dimensions, the y and z dimensions, and the x and z dimensions. The formula for covariance between two dimensions is given as covariance xy is equal to 1 by n minus 1 summation I is equal to 1 to n x minus x complement into y minus y complement, where measuring the covariance between x and x or y and y or z and z would give you the variance of x and y and z dimensions respectively. Representing covariance between dimensions as a matrix, example for 3 dimensions we have C is as this matrix here, which is matrix of covariance between dimensions. So here this is x, y and z on the column side and same x, y and z on the row side. This is a 3 by 3 dimension between 3 by 3 matrix, I'm sorry, between the dimensions. Diagonal elements are the variances of x, y and z. So variance between the same dimension, covariance between same dimension is the variance of x, variance of that dimension. Covariance of x, y is equal to covariance of y, x, hence matrix is symmetrical about the diagonal. N-dimensional data will result in an n by n covariance matrix. Eigenvalues and eigenvectors. In linear algebra, an eigenvector or characteristic vector of a linear transformation is a non-zero vector whose direction does not change when that linear transformation is applied to it. Formally, if T is a linear transformation from a vector space V over a field F into itself, then V is an eigenvector of T. Mathematically, T of V is equal to lambda V, where lambda is a scalar in the field F known as the eigenvalue, characteristic value or characteristic root associated with the eigenvector V. Suppose we need to find eigenvalues and eigenvectors for matrix A. Find lambda into I, where lambda is variable of eigenvalues and I is the identity matrix for matrix A. Set A minus lambda I is equal to 0 and solve for lambda. This will give us eigenvalues. Next, set A minus lambda I into V is equal to 0, where V is an n by 1 matrix of variables of eigenvectors V. N is the number of rows of matrix A. And solve by Gaussian elimination for V. This will give you eigenvectors. So we have discussed all of this in the mathematical preliminaries. Algebraic interpretation in one dimension. Given m points in an n-dimensional space for a large n, how does one project on to a one-dimensional space? So we need to transform the high dimension into lower dimension, one dimension that is. So we proceed using this following algorithm. Choose a line that fits the data so the points are spread out well along the line. So we make a line here so that the points are well spread out along the line. Next, Formally minimize sum of squares of distances to the line. So we use sum of squares because it allows fast minimization assuming the line passes through 0. In this example, we see a three-dimensional reduction to two-dimension. So in three-dimensional space, our initial set is here as depicted by diagram A. In diagram B, we take three principal components PC1, PC2, and PC3 in X, Y, Z directions. Out of that, we choose the PC1 and PC2 components to reduce this to a two-dimensional feature space. Data reduction. Summarization of data with many or p variables by a smaller set of k derived or synthetic composite variables is data reduction. So in n by p dimension, suppose we are given a set A of data, it is reduced to n rows of k features where k is a subset of p or a synthetic composite set of p, and it is finally it gives us the output x data set. Principal component analysis. As discussed in few previous slides, we reflected on what PCA is, or principal component analysis is. It is a way to reduce data dimensionality, where we are given higher dimensions of data, we convert it to a lower dimension data. PCA projects high dimensional data to lower dimension and thus converts many features into smaller features. PCA projects the data in the least square sense, that is, it captures big principal variability in the data and ignores small variability. So the more the variance in the data, it captures that, and it ignores small variability. Now we discuss PCA's first algorithm, or the sample covariance matrix method. Given data x1 to xm, compute covariance matrix summation as 1 by m summation I is equal to 1 to m xi minus x complement into x minus x complement transpose, where x complement is equal to 1 by m summation I is equal to 1 to m xi. So PCA basis vectors is the eigenvectors of summation. Larger eigenvalue implies more important eigenvectors. So the more important eigenvectors are the more having more variance or larger eigenvalue vectors in this set that are chosen in the final model. Next is the second PCA algorithm, or the SVD of the data matrix. In this, we have the data matrix X, and we take the singular value decomposition of X we do with USV transpose, and we proceed with the algorithm. So columns of U are the principal vectors U1 to UK and orthogonal and has unit norms. So U transpose into U is equal to identity matrix I. We can reconstruct the data using linear combinations of U1 to UK. Matrix S is diagonal on the other hand and shows importance of each eigenvector. And columns of V transpose contain the coefficients for reconstructing the samples. U reduce is U and from 1 to k, and Z is U reduced into X, and Z is the final matrix with reduced dimension. So this is the working of the SVD method. How to choose the value of k, that is the number of principal components. K should be smallest such that average squared projection error divided by total variation in the data is less than 0.01. 99% of the variance is retained in this case. So this is given by this equation here, and this can be simplified further to this. If this is less than 0.01, implies that the variance is 99% retained. Applications of PCA. It is used in data visualization, data compression, or reduced memory space needed to store data, data compression by speeding up your learning algorithm, or dimensionality reduction for reducing dimensions of data.